I've been reading papers. Research group and out of this set of centers here for quite some time, and it's nice to actually meet the faces and get to talk about this stuff. So yeah, I'm originally from the US. I've been in Germany about 20 years. I've spent the last 2 of those running this research group at Humboldt Center Herion near Hamburg. And I want to talk today about, well, specifically deep differentiable emulators, mainly related to 1 or 2 papers that came out last year, but also how they kind of fit into bigger plans for what we can do with differentiable ML models in the geosciences, what we're doing, what other groups are doing here, as well as a lot of other places, and what the future might look like for this little intellectual project. So a lot of the computational tasks we might want to solve in the geosciences can be expressed in the language of state space modeling. We have a system state X at each time point, which represents, say, a physical snapshot of the world that we're modeling, the simulation world. It could be a grid with multiple Z levels of pressure, temperature, wind speed, moisture, what have you, and it's a snapshot for 1 time point. And the state space in the state space model means that we have a time stepping function where each time point is providing the only guidance for the next time point. So there's no kind of a larger historical effects that are indirectly affecting the next time step. We're saying everything evolves as a function of the current state. And so in the simulations that we build in this framework, we have an update function which would express things that we have a physical understanding of: fluid dynamics of the atmosphere or ocean, physical processes, often things below the grid scale that we want to parameterize, radiation, turbulence, phase changes, and important tracer advection as well. Okay, so I want to talk about deep differentiable emulators as a potential solution to 3 main optimization tasks that arise as inverse problems in the geosciences. First of these is data assimilation. So given a series of observations that we can make from the system, which are generally noisy and incomplete and not a perfect representation of what's going on in the system state, we want to choose an initial state for the simulation such that it matches our observations. The second we might like to do is model tuning. So given a model class which has some free parameters, which might represent something like, a diffusion coefficient in turbulent heat exchange, or the rate at which, ice crystals fall in clouds, or the albedo of fresh snow, or anything like that, we want to choose these so that our predictions match observations. We want to choose the parameters of our simulation models, which are generally few in number and physically interpretable. And the third, I think, most ambitious task, and indeed there's been a lot of work from this research group too on this, very successfully, I think, is learning corrective terms. So the idea being that we don't only want to tune the models we have, but we want to add additional terms to their time stepping functions or differential equations to get a better match from predictions to observations. And why would we want to learn terms with a general, say, data-centric model as opposed to physics? Is because there's a lot that we can't represent in a first principles physical representation, such as processes we simply don't understand, for example, the biosphere, or subgrid scale processes which we can't afford to represent in explicitly. So in all 3 of these problems, if we want to solve them as gradient-based optimization problems, we need to differentiate through the time stepping function of the simulation with respect to its inputs in order to optimize our predictions with respect to the initial state, the parameters, or the parameters of the simulation, or the parameters of a corrective term. But in practice, for many important simulations in the geosciences, these derivatives simply aren't available. So the idea of deep differentiable emulators was one way of getting at them in order to be able to solve these optimization problems. And I'll start with data assimilation. I'll talk about that the most. though I think you'll hear about a lot more about that in the fourth lecture, and kind of a broader range of approaches as well. So again, the basic idea is we have observations which give a noisy and incomplete representation of the system state. We have an unknown initial state for which we may have a prior distribution, some previous expectation of what it ought to be. And we want to find the initial condition which matches our prior assumptions as well as our observations. And then having done so, we should get a good match to observations that we have. And then if we carry the simulation further in the future, we hope to get a good match to observations we don't have yet. So that would be analysis and forecast. So to formalize this in a mathematical sense, for example, this is the framework we adopted, but it's by no means the only one. We have an initial state with a Gaussian prior. It has a mean XF and a covariance B. For a given state, we assume that the observations Y, given the state X, are Gaussian with some known but possibly nonlinear function h of x and Gaussian covariance R. So what we want to do then is carry out maximum a posteriori estimation, which is to say we want to find the initial state with the highest posterior probability given the observations and prior assumptions. So that breaks down to maximizing the log likelihood of the observations given the initial state, as well as the prior probability of the initial state, plus a constant term we don't care about. So we maximize that or minimize its inverse, and this is our data assimilation loss. And this corresponds to a hard constraint for the Vera scheme, by no means the only approach, but the one that we wanted to pursue. Because I thought, in particular, because this was, we thought, a great way to demonstrate the capabilities of ML for learning to differentiate simulation models. So then when we expand this according to our assumptions, we have a data mismatch term. Here are observations minus the predictions from our model. We take the initial state, we iterate it out to the time stepping function n times, put it through the observation function, compare it to the data. And then we also have a prior term as well over here. Okay. Yes, get my mouse here. So how can we minimize this? I'm going to go over some kind of standard strategies that are in use, and then I'll explain exactly what we wanted to do with machine learning instead. So a common thing, like you might see in many operational weather models, for example, you would see this at ECMWF, is, well, if you want to minimize this loss function, you can you'll need to differentiate through it. And for this, you can write a routine along with the rest of your model, say in Fortran, to do so. So we calculate a Fortran routine, which, given the input, calculates not just the output, but the derivative of the output with respect to the input, often using some approximations, maybe a lower spatial resolution, but this allows us to solve these optimization problems. In fact, ECMWF uses a weak constraint scheme, so slightly different than this, but basically the same idea. This is one way of doing things, but it requires a lot of investment of time, of money, and it reduces your flexibility to experiment with new model formulations, because then you have to kind of maintain this delicate adjoint code, which would calculate your derivatives. Another thing you can see in the literature for very small, simple models is simply to use finite differences. So if we want to differentiate through this function to solve the optimization problem, to do data assimilation, we can simply make small perturbations to the inputs. This only makes sense in very small systems, but you can find a few articles which have applied this. A third strategy, and I think this is what we'd like to be doing, but I think there are good practical reasons to say this is not going to happen in the immediate future, is that our entire simulation should be written in a framework which supports automatic differentiation, PyTorch, Julia, JAX, TensorFlow, and so on, right? So if we express all the logic of our simulation in a differentiable programming framework, then we can get the gradients for free and use them to solve these inverse problems, to do data assimilation, parameter tuning, and so on. There are a few simple examples of this in the literature, not many. there is this ocean model, a kind of a very simple Boson-esque approximation developed by scientists at MIT and Caltech. And they've done a few very simple studies. It's not really approaching anything like the realism or complexity of an operational ocean model, weather model, climate model, but it's kind of a nice playground to do proof of principle studies. If you can make this work, of course, you get a lot of bonuses, like you get very good hardware support, and you get all the software updates of kind of a modern library. You're not using bits of Fortran code from the 70s in your model. But in practice, to do real earth science in the software and hardware environments that we do is just not going to happen probably for the next 5 or maybe even 10 years. And there are some tools indeed for automatically differentiating Fortran code as well, but they tend to be very efficient. They don't scale to large models, and they're based on static code analysis as opposed to the efficient backward pass of machine learning. And then a fourth strategy, which, for example, is used by the German Weather Service, is instead of solving the optimization problem through a gradient-based approach, you can use an ensemble. And you can use an ensemble Kalman filter, which is way beyond my scope right now. But the basic idea then would be to use an ensemble to get a similar effect without having to differentiate through your model. And indeed, this is what some climate and weather models do. So there's nothing wrong with any of these, and they all have a lot of promise. And there indeed are some great approaches with ML using these strategies as well. But what we wanted to do, both for DA and kind of maybe for other further problems downstream, is to say, suppose we have some simulation, which we can run. We have the code for it, but we don't have the derivatives. Can we use a neural network to obtain those derivatives to then solve the inverse problems, such as data assimilation that we want to solve? So the strategy overall would be this. We can run our simulations with various initial states. We get the sequence of system states by running a simulation. We then use those simulations, which incorporate all our scientific knowledge in their code base, essentially, to train a neural network to emulate the state update function. So I'm showing one convolutional network here. I'll go into the question of architecture choice more a little bit later. But the basic idea is we want the network to estimate these time-stepping schemes. Given an input, we want the neural network to make the same output that the simulator would have. And then, having trained this on simulation data, we use the natural differentiability of the neural network to get the gradients we want for our inverse problem. Now, this is work that was mainly done by Marcel Nonnenmacher, a postdoc in our group. And the key thing here is we're using the differentiability of neural networks in two ways. First, when we train it, right, we have the simulation data and it has all its free weights and biases and so on. So we have to adjust it. And second, after we've trained it, we fit those weights and biases, we now are going to optimize over the input to the network. And this will allow us to solve our inverse problem. So to train it, we can use a very simple least squares objective. Given each time step, we should then compare the output of the network to the system state on the next time step as calculated by the simulation. So basically, we're saying, given the same input, the simulation and the emulator, the neural network, should provide the same output. So then, okay, we wanted to test this, first of all, in a simple toy model. We settled on the Lawrence 96 model. We wanted something where we could easily calculate the true input-output derivatives to see if our neural network was given the right answer. We wanted something where we could adjust the system size, and we wanted something simple. So this is basically, it's a very interesting paper that actually introduced it, but it's basically a simple model of something sort of like advection, not really, where we have a system of coupled ordinary differential equations are on this periodic ring. And each one of them is the time evolution of each location is affected by its neighbors. and there's a constant forcing term. And it's known to have chaotic dynamics. So for F equals A, which we mainly use, we use the layup of time of about 1.67 units. And so here's how these 40 different variables evolve over time. And if we kind of unroll this into a plot with time on the x-axis, and we kind of unwrap that periodic ring on the y-axis, we get a plot like this with these waves that persistently travel in one direction. So this is a differential equation. To actually do the simulations, we also need to integrate it in time. And following Lawrence in his 1996 paper, we just use a simple explicit fourth order scheme, a Runge-Kutta scheme, to do the time integration. So here's our simulator, and we want to ask if, in this very easy case, if we can train the neural network to imitate the time stepping scheme of the simulation, could we then use the derivatives, the input-output derivatives of that neural network to do data assimilation in this system? So we have to design a neural network. So what are the considerations and what are the kind of degrees of freedom that we have in designing that? I mean, the standard neural architecture questions, the number of layers, how many units do we have in each layer? What are their activation functions, ReLU, TANH, LU? And, of course, we can just think of this as some big data-centric problem, and we can do hyperparameter tuning. We can see what works and what doesn't. But in the case of Lawrence 96, and I think in the case for most simulators that we want to emulate with a neural network, we can often make informed choices by looking at the structure of the simulation. So, for example, we know from the fact this is an explicit scheme and only has local interaction terms in the time derivative that it would be nice to have local causal structure in the class of functions we're using to imitate it. So we can achieve this by using a lot of one-by-one convolutions, which kind of act as sort of fully connected layers, and only a few that involve input from neighboring units. We have the fact also that these dynamics are spatially invariant. So the fact that we use convolutional layers at all will kind of give us that invariance. And we could go further, and we explored this in the paper, but I won't go into it, but you can go even further and like looking at kind of bilinear layers to capture the exact mathematical structure. At that point, it's sort of cheating, and we mainly focused for that reason on more generic deep neural networks. But overall, we can use partial knowledge of the simulator in designing our architecture, and indeed we're going to, as has been shown by several papers, including I think from here, you can often gain an advantage instead of just by outputting the next system state. You can take your neural network and put it into the same Runge-Kutta scheme, and that's what we did as well. And this gives slightly more robust results. So then this is how it looks when we actually try this. Here's a simulation, and here's below it is what we call the emulation. Basically, we iteratively apply the trained neural network with the same initial state, and indeed we get a pretty good match. Eventually, they do begin to diverge. You can see this big difference, remembering the layup of time is about 1.67. So because it's a chaotic system, this has to happen at some point. And with a better network, this might happen later. With a worse one, it might happen earlier. But what's encouraging also is that even after we do get this divergence, we don't see some kind of blow up of the values of the system. It doesn't diverge numerically. It still sort of looks like a Lawrence 96 simulation. And so we also found that the rate at which the error between the simulation and emulation grows over time, it can be reduced somewhat by including more training data, but this does begin to saturate at some point. And I'll get back into this issue, I think, a little bit later. But overall, we see some benefit, but a saturating one. But okay, we can kind of imitate the time stepping scheme of the model we trained on, but that's not really what we wanted to do. What we wanted was to get the derivatives accurately so that we can use these to solve inverse problems. So how accurate are these derivatives? This is really what our first big question in kind of asking, would this approach work in this very simple model? So if we look at a single time step, we're looking at x of time t and x of time t plus delta. We can calculate the input-output Jacobian, and they look pretty similar. If you look at the numbers, there are some slight deviations, but overall these deviations are about 10 times smaller than the derivatives themselves. So it's kind of giving the right thing. But how accurate this will be in when we actually use it to solve the inverse problem remains to be seen. And of course, we're not just interested in predicting the next time step. To solve inverse problems, we have to self-iterate to predict many time steps in the future. And so here, if we look at the red cross in the bottom plot, if we look at this output, we can calculate the derivative of the system state at this location on the y-axis with respect to every other location and every other time in the past. So all the way back to the beginning of the simulation. And you can see we get this kind of this shape where there's a positive or negative dependence of this value on others. We see this kind of asymmetric expansion of the region which affects this point, which is consistent with the asymmetric traveling waves in the simulation. And you can see this is pretty well represented when we use the self-iterated emulator compared to the simulation. And again, we have differences, but they're overall about 10 times smaller than the actual derivatives themselves. If we look at the Frobenius norm of these input-output Jacobians, we see actually even up to a much larger training set size, we're gaining benefits after the error was already sort of saturating for the error in the time steps. But okay, so we have our input-output derivatives. We can now differentiate our loss and solve our optimization problem. So again, we're using a simple toy model for simulations. In this example, so we actually know the ground truth, which wouldn't always be the case. And then we want to say, okay, what if we have this trained emulator, which was trained on simulations, but now what if we don't have access to the ground truth simulation data? What if we only have a noisy and incomplete observation of the system state, so that each time point we're, in this case, only observing 25% of the values, and we're doing so with Gaussian noise. And so we have an integration window here in orange where we have access to the data, and we want to see how well can we then solve an inverse problem to reconstruct the system state in that window. That would be an analysis. And how well can we forecast the system state in the future? And indeed, it actually works pretty well. You see, at least visually, a pretty nice resemblance between the ground truth and the reconstruction when we solve this optimization problem. But the real question is, how well does this work compared to using the true derivatives, which we do have access to in this very simple toy model? And I actually really didn't believe this for quite a while when we first saw it. It seemed a little bit too good to be true. The very surprising thing is, despite the fact that we have significant errors in the agreement between the simulation and the neural network when we self-iterate 1.5 and 2 time points, we don't really see any difference. The chaos that makes the data assimilation difficult seems to do so just about equally well for the simulator and the emulator, such that the errors that the emulator makes don't seem to make any difference. So to be a little more explicit here, this is the original true simulation. Here's the data we have access to. This is a reconstruction we get when we use the true derivatives and time-stepping function of the simulation. And this is a reconstruction that we get. You can see we're pretty much perfectly reconstructing the analysis. And as we go into forecast mode, even when we have access to the ground truth simulation, because our observations are noisy and incomplete, we eventually make bigger and bigger errors due to chaos. With the emulator, we're getting basically the same performance. We're getting a near perfect reconstruction during the analysis, and we're seeing errors that grow. So we can ask a couple questions here. What about the optimization problem itself? We wanted to reconstruct the initial state. How well are we doing that? In fact, we're doing it very well for both the emulator and the simulation. Then, if we look within the analysis window, how good is our reconstruction of the simulation state as a function of how big that window is? That is, how much data do we have access to? And we can see we get an improvement. But remarkably, it's basically the same using the true model and the emulator. And then again, if we want to predict in the future, we get bigger and bigger errors the further we go. But what we're showing here is that basically in this toy model, in this simple case at least, we're able to solve this optimization problem as well as if we had the true simulator derivatives, which was very encouraging. Okay, so this is one inverse problem that you could solve using these deep differentiable emulators. And so beyond this kind of proof of concept, we wanted to look at one of the other optimization problems in the same system. So as I mentioned, the Lawrence 96 model has this free parameter. This is a simple one-level model. We'll get to a more complex version soon. It has a single free parameter f, and the bigger this f value gets, the more irregular and chaotic the system becomes. So for very low f values, almost sort of laminar, if you like, whereas for high values, it really is spatially heterogeneous and harder to predict, and it has a shorter layup enough time. So here the idea was, well, what if we train a neural network to predict the next time step again, but now instead of simply providing the previous time step, we also provide an additional channel, which is simply the parameter value f at all spatial locations. We train it now using a collection of different simulations with different f values. And having done so, again, looking at noisy and incomplete data, we can ask, can we reconstruct the correct parameter that was used to generate a simulation? So if we have a noisy and incomplete observation of the system, we can solve our optimization problem, which in this case reached a close but not identical value of f. Right now we're optimizing over the initial state and the free parameter of the system. And we can see that if we plug in an f value which is too low or too high, we'll get something which is not visually consistent with the simulation. But overall, solving this optimization problem using this emulator trained on multiple, we'd call a conditional emulator trained on multiple parameter values, we found that overall you can reconstruct the free parameter of the system pretty well. So this could be a useful tool for tuning models where we don't have derivatives. That is, if we can scale it up beyond the simple toy model case, which I'll get to in a moment. Yeah.
In these experiments,
yeah.
Maybe the first ones during the hard constraint.
This is all hard constraint.
Or is it hard constraint?
Everything is hard constraint that we're doing. Yes, we're looking at other data simulation schemes now. In particular, we constrained 40 bar, but all these experiments were hard constraint. Yeah. Well, I think, and the reason I think also for that was because we really wanted to choose a task that emphasized the need to have these input-output derivatives. I think in weak constraint, you can kind of get around it in various ways, more or less. And we're very interested in trying to build models which are which can be self-iterated.
And you have no diagram prior.
Oh,
only the dynamics. Observations and then
we often do have a prior on the initial state, but I think it's a very weak prior. In fact, we found it didn't matter if we turned it off.
Okay.
Yeah. Yeah, I won't cover it today. We did start looking at chunks and model error terms, but I won't get to any of this now in this talk. Okay. So in the third optimization problem, we'd like to learn a corrective term. So as I mentioned, there's a two-level version. So basically in the one-level version is right here, and then we have an extra term. So we have slow variables x in blue and fast variables z, here's head there, y in orange. And basically the slow variable is forced by the mean of the nearby fast variables, and the fast variables have a similar kind of time evolution, but they also receive input from the nearest slow variable. So you have these slow and fast timescales, these fine and coarse spatial processes coupled, as you do in, say, a lot of fluid dynamical systems. So this is the model. And of course, as in, the atmosphere of the ocean or airfoil simulation, you can just resolve everything if you're willing to pay the computational cost. But is there a way that we can get a model that includes only coarse variables to behave as if it were coupled to fast variables that we don't explicitly resolve? Is there a way to get a model with only the blue to behave like the blue and orange together? Can we learn a correction B psi of x, which has its own parameters, such that it behaves like the coarse variables of the full model? And so we pose the differential equation this way. Here on the left-hand side, you have the full fine scale model. Here's the coarse scale model, where we replace the forcing from the fine scale variables with a function of the coarse scale variables. We're trying to guess what the effect of the fine scale variables is from the state of the coarse ones. And again, in order to train this, we need to take derivatives of the input-output function of the simulation, which again we do using an emulator. And the result is what we call in the geosciences of parameterization, this additional term, a function of the system state, a local function of each point, which causes a coarse scale model to behave as if it were coupled to a fine scale one. And other groups have done this as well, with a whole bunch of other techniques as well. But what we wanted to emphasize here is using the derivatives from the learned emulator to actually learn this parameterization. And it did work for this task, again, in a very simple toy model. So, okay, what is this good for? What can and it can't do? And how does this fit into kind of the larger picture of how we want to use ML in the geosciences? We definitely don't want to stick around with kind of toy models. It's kind of neat that we use this to differentiate code that we can run by training on the simulation data. But what are the limitations, and what do we want to do with these ideas? So, I mean, the main issue is that we have all this physical knowledge about the system, conservation laws, mathematical equations, symmetries, and we're basically discarding that. We're saying we're going to learn the time stepping function from scratch. We're going to learn what we already know, essentially, basically because we don't want to translate 500,000 lines of Fortran running on the high performance computing cluster into PyTorch or Julia. So we're losing out on a lot of hard work and a lot of scientific insight. I've showed you this for toy models. I'll show you this for some more complex models, but I mean, it really, if you want to learn from data, then the number of interactions really limits your ability to scale. When you have a lot of variables that can all affect each other, the amount of training data you need and the amount of compute you need to effectively learn this to a level of accuracy that will let you solve these optimization problems it can be prohibitive. So it's difficult to scale. So can we do anything about this? Well, a little bit. One thing we found in the Lawrence 96 cases, I mean, it's a nice toy model in that you can really adjust the system size. So we tried running simulations where the system state was maybe 600 or 1,000. And we find that by just training on randomly selected local patches, because the time stepping function is all local in both the emulator and the simulation, we're able to get very good emulators that way without loading the entire system state in memory. So this is maybe a strategy for scaling up to larger models. The interesting thing is that the optimal emulator learning actually works with a batch size effectively of less than 1. If you think of the full system state as one batch element, it's better to use less than 1 full batch size. Okay, so this is a neat trick, but when you think about the kind of computations we really do in operational models of the atmosphere and ocean for climate, for weather, I mean, the scale is just is completely immense, even really beyond the if you think of not training but inference, is well beyond even the very largest of the large machine learning models with billions and trillions of parameters. When you have this many grid cells, Z levels, multiple variables, and a lot of computations to do, you have just a lot of yeah, so basically something like 1-2 trillion values are computed per simulated day in these very huge code bases on these very complicated, specialized hardware systems. So the idea of just scaling up data, data-driven ML, whether it's this emulation approach to inverse problems or trying to replace parts of the model without any scientific insights, I think a lot of people would agree is naive, and I would argue that as well. So in the rest of this talk, I want to talk more about where we go from here with these insights in mind, knowing that we want to solve these inverse problems. We want to improve our models. We want to tune them. We want to do data assimilation in them. But simply scaling up a data-centric view isn't going to work. So what are the other kind of scientific insights, or in the language of machine learning, inductive biases that we're working to put into these ML models? What are some other groups doing as well? And in the third part of the talk, I'll talk about basically the challenges and kind of opportunities and current efforts to learn just subcomponents of a larger model using ML. I think this would be a good time for a short break.
15 minutes for break. There's coffee and I just pause the video here.
Right. So thanks. So now I was just getting to the point of the limitations of this purely data-driven view, where we're just going to learn everything and have our machine learning model do the work. And I was talking about how it won't scale to more complex and costly scenarios. So I want to take a step back about 100 years. 100 years ago, Lewis Fry Richardson published Weather Prediction by Numerical Process. For a book about weather prediction, it has a really, actually pretty exciting description to start off. And he starts off telling how they predicted weather in the city of London in 1922. Can you guys see, or is this too bright here? Yeah, so what he's showing here is one of these maps they use, right? So they had these observation systems, observation stations all across the continent, all across England, where they would measure temperature, pressure, wind speed, so on. They would they would send in these measurements by telegraph to the central London office, where they would put them on a map. And then they had a big book of these maps, these giant maps, and they would look through the book and say, oh, well, last July, there was one day that looked like today's map. What happened that evening? What happened the next day? And they'd forecast the weather, basically what we'd call an ML pattern matching. But 100 years ago, Richard said, actually, there might be a better way. We have all these equations about fluid dynamics, about temperature, about pressure, about wind speed. We could actually use, as crazy as this sounds, differential equations to predict the weather. And he pictured this giant room full of people doing all these calculations by hand. It's a very nice thing about this book is, even though computers hadn't really been invented yet, he was able to open source his code. He had all these worksheets he included in the book that you could kind of fill out, and you fill in the blank spaces and do the calculations he would tell you to do, and you could do these predictions. In the end, it didn't work. He went a little too far from the data, and people hadn't thought about data assimilation. But it was a really important idea that kind of provoked a lot of the thought that ultimately led us to where we are in Earth system modeling. Very interesting guy himself too. But So we have these two streams of thought. I mean, going back to Richardson, we have the physics-based approach and the telegraph map. And 100 years later, we're kind of in the same situation, right? We have, so let me just quickly check battery. I think I'm okay, yes. We have machine learning, which is efficient, which uses our hardware well, which is differentiable and high performance. And it kind of deals with new data very easily, but it lacks interpretability. And it tends to generalize poorly, not necessarily to new held out data, but to new scenarios. It can interpolate, but can't extrapolate. On the other hand, we have physics-based, chemistry-based, biology-based numerical simulations where the processes, parameters, and state variables are interpretable. They're often physical. And by incorporating all these conservation laws, symmetries, and so on, we're able to generalize much better to new scenarios. But as I mentioned, because of the way these are stated as, say, PDEs that have to be time integrated or complex, these beasts of hundreds of thousands or millions of lines of Fortran code running on a cluster that's heating up half the city, it's very difficult to use these flexibly to fit data and to solve the inverse problems related to data assimilation, parameter tuning, and improving the model with corrections. But nonetheless, we've used these to kind of build these objects, these simulations, which incorporate a lot of our knowledge that have really been hard won over the last 100 years. So question is, how can we combine these? Can we combine these to try to incorporate the best aspects of both? So I'll start sticking a little bit with this emulators idea, and I'm going to go with a kind of a more difficult case where we found that the data-driven approach really failed us. It's embarrassing. It's not actually that much more difficult than L96, but we found it very hard. And then I'll talk about how using some of the ideas from physics-based numerical simulations inspiration helped us to build a better emulator. So we're just in the shallow water equations. You have this very simplified view of kind of vertically integrated Navier-Stokes, where you have in the 2D case horizontal and vertical velocities and height, so u, v, and zeta. It's a pretty simple differential equations. Linking them, there's more and less complex versions with different terms. What I'm showing you here is a scheme from the late 80s, which was designed for the oceans. If you're from North Germany, like me, you can recognize the geography on this low resolution grid. Hamburg is somewhere down here. It's a semi-implicit scheme which deals with the stiffness that arises between the land-sea boundary, and it's good for simulating these systems. It was kind of considered a breakthrough when it came out in the 80s, and a number of people still use similar things today in kind of coastal research. So a natural question was, can we approach this as a very simple model? I mean, compared to like an actual ocean model, it's extremely simple, but it's a lot more complex than L96. Can we try to solve, can we even try to build an emulator which would work when training on the system? And the answer turned out to be a pretty resounding no, right? So we did the time integration of this system. Again, I think it may be a little too bright here, but you can see this ripple, which is spreading out and bouncing off the walls in the shallow water equations. And then we have an emulator, which was trained on these time-stepping schemes. We threw a lot of data at it. We threw a lot of compute at it. We threw, many GPUs and different architectures. But what we found is a consistent problem where these numerical modes or artifacts which kind of emerged and got worse over time and really never went away, which really prevented us from using the trained emulators to solve inverse problems that involve time horizons longer than a few time steps. So we were puzzled by this, and then there's one of these things where you think about it and you think about it and you're like, oh, okay. Well, when you put it that way, it's actually sort of obvious. And it comes down to the nature of the time integration in the simulation we were learning from. So we're interested in learning a time stepping update for our system state, which consists of height, vertical velocity and horizontal velocity, or rather height, meridional and zonal velocities, right? We have longitude, latitude, and we have a grid. And we want to predict the values at some point in this grid. We have a partial differential equation. Generally speaking, we have local interactions. So the time derivative of the function at one time and location will be a function of those values and their spatial derivatives and perhaps higher derivatives and so on, right? This is kind of the standard fluid dynamical PDE that you might see. Okay. In order to actually integrate this, our simulator has to be discretized. So in order to calculate the spatial derivatives, we have to discretize space. We also have to discretize time. The simplest way of doing this would be a one-step explicit Euler integration, right? So we have a tendency function, the time derivative as a function of the local state and its spatial derivatives. We calculate that, multiply by the time step, add to the previous state, and we're done. That's the simplest possible time integration scheme. All right, well, maybe that's not accurate enough for us. We want something like Runge-Kutta 4 or something more, which will allow us to use larger time steps without diverging. So we might use a second order method, right? So here, what we do is we first calculate the derivative of the old state, and we multiply that by half a time step, add that to the old state, and then put it through the derivative function again, and then multiply that by a whole time. So this is one second order method. There's many different ones. And now look at the dependence on the input in each of these cases, right? Here's the output cell we're trying to predict. For the first order explicit, we have this dark blue region influencing this output, and for the light blue region for the second order. And this is just simulation. We're not talking about any ML. But now let me jump back for a second to this semi-implicit scheme in Bachhaus. The trouble is that you see the heights and velocities at the new time step, n+1, on both sides of these equations. It's a semi-implicit scheme. What that means is the new state, which we're trying to estimate, oh, this one is smart boards and you shouldn't touch it, appears on both sides, and we have a system of equations that have to be solved for it. We can't simply compute everything in a feed-forward way as we would for a first or second order explicit time integration method. In this particular semi-implicit scheme, we end up with linear equations. In a more general implicit scheme, they might also be nonlinear equations. But the point is, because we have these linear equations, x n+1 and the new time step n+1 appears on both sides, and the output now depends, at least in a technical, strict mathematical sense, on all elements of the input. And when you have this all-to-all dependence, CNNs begin to scale poorly with the size of x, because as the size of x grows in the latitude and longitude directions, you need either bigger convolutional kernels or deeper and deeper networks, which get harder and harder to train in order to capture this all-to-all dependence. And the worst thing is, it's not even, well, okay, you need a kernel size of 3 or 5 or 7, because the coefficients of this linear system depend on the previous state. It's all data dependent too. So it's difficult to know exactly how wide your architecture should be. So this led us, when we realized this is what was getting to us, we and it wasn't just, oh, we had this flash of insight. We looked at inputs and outputs. We looked at particular cases where the emulator was failing. We gave it delta functions and so on. It led us to rethink the kind of the neural network modules, the layers we were using to build our architectures, just as I talked about in this kind of more, I don't want to say totally trivial, but obvious way. Well, spatial invariance, therefore convolutions for L96. We were able to do something similar here. to look at the kind of system we're trying to learn and say, what mathematical modules should we put into our neural architecture? All right, so we have a fully connected layer. Input vector X with M elements, M by M matrix A, and then we get Y. And then, of course, we can put that through our ReLU or 10H, whatever we like. Everything connects to everything. Well, we'd like to be more efficient than that. We'd like to scale to, large X. We'd like to have spatial invariances. We can use a convolutional layer. So here, instead of an M by M matrix grows with the size of X squared, we have a K by K convolutional kernel, which doesn't grow as the size of X increases. So we can learn local rules and then apply them to even bigger systems than we trained on. We can think of this convolution as a matrix vector multiplication as well, in which case the equivalent matrix C is very sparse. It has only on the order of the number of non-zero elements is linear in the size of X, not quadratic as it would be for the fully connected layer. All right, so the idea here is, what does the simulator do that the neural network can't? Well, practically, it has all-to-all dependence, but more explicitly, it solves a linear system. So what if we also solve a linear system? Given our input X, what if we compute a matrix A and a vector B and then solve this? And in particular, not just any matrix, but a matrix which has the same sparsity structure as a convolutional kernel. Not necessarily the same spatial invariance, right? Because these coefficients are going to vary in space, just as the coefficients of the linear system for the, if we look at the semi-implicit scheme, we find the coefficients that get multiplied by the states also are spatially dependent. So we want to have coefficients in this matrix, which are local functions of X, which depend on X, but which only have the same sparsity as a convolutional layer. So how do we do this, right? Because, okay, X here is sort of I've labeled it as an M by 1 vector, but it's really a representation of an unrolled image. So how does this work? We have our input fields, velocity in the meridional and zonal directions, height of the water surface, whatever. And then in later layers of the network, we'll have more than we'll have any number of channels we like, right? But we have a bunch of them, right? That have been calculated as the output of convolutions. And now we're going to split them into two groups. Some of them will just pass through this implicit linear layer. And then we're going to take 5 of them to define a 5-point stencil. So we have different channels of activations, and we're going to define a system of linear coefficients where the unknown variables get multiplied by a matrix A. And we only have 5 diagonals of this matrix which are non-zero. We have the main diagonal, that's this point in the stencil. And then we have, assuming that you have a column first indexing for your image, then you'll have, this will be one above the diagonal, this will be one below, and then these two will be off to the side. So we have these 5 stencils in a cross-shaped, 5 points in a cross-shaped stencil for a convolution. Could also be 3 by 3, but we just used a 5-point stencil here. And this gives us 5 non-zero bands in this banded matrix, this very sparse banded matrix. So the idea is we have our image with multiple channels as we move through our network. We use 5 of these channels to define these 5 spatially varying coefficients. We use a 6th one to give the vector B, which is the unrolled spatial field for the constant term in the linear system. And this defines a linear system, AY equals B, that we can solve for Y. And then we have additional channels which get a ReLU, and we just put them together. So we're using up essentially 6 of our conv channels to build a linear system, which we then solve. And this is a motif we can put in our network wherever we like. We actually used it in this study in the output. So it's kind of the high concept idea. Let's get a little bit more into the equations to understand what we're doing and maybe a little bit about why. So as I mentioned, the matrix we're defining is banded. Here's a 3-band case, which would actually correspond to a 1D shallow water equation. I guess if you were to implicitly solve Lawrence 96, you get something similar. But the idea is most of these values are 0 in the matrix A, but not in its inverse. If you were to invert the matrix and just say, okay, you could calculate, y equals A inverse B, but then you'd lose out on the sparsity and you'd pay this terrible memory and computation cost that you would with fully connected networks. Actually worse, because just computing this is size of x cubed. All right, but so what are we doing? We're saying the matrix A consists of some of these bands, and each band is either a diagonal or an off diagonal. So you have these integers 0, 1, -1, and these are 0 is the main diagonal, 1 is above, -1 is below. And then you have functions given x, you're going to calculate the coefficients along here. In fact, these will be local functions, so the coefficient in one location will just depend on x at nearby locations. Similarly for b. And then we end up with this linear system. Now, we could solve it using a matrix inversion. We don't want to do that for reasons I just mentioned. We could be a little more clever and use an LU factorization or some other factorization, which have slightly better properties. But we don't want to do that either. I mean, that's what you do if you just call, say, torch.solve in PyTorch or the equivalent things, right? That might work for 1D systems that are pretty small, but we want this to scale to really big systems when actually X and Y are really the vector forms of these unrolled images. And maybe images even begins to, we're talking about, many points in a grid with multiple Z levels in 3D. We have really big states, and we don't want to factorize these matrices every time we go through this layer of our network. Instead, we use an iterative solver, basically saying, given an estimate of Y, even though it's a linear system and we can solve it in closed form if we wanted to, for large enough systems, it's more efficient to use something like conjugate gradient or red-black Gauss-Seidel. And we use red-black Gauss-Seidel in this study. And the advantage of this is we never have to factorize A. We don't have to invert it. We only have to calculate A times Z for a bunch of vectors. And because A has this banded structure, that's really easy. All you have to do to calculate A times Z is shift Z up and down along its array axis and then multiply it by the different diagonals. So this lets us do very efficient matrix vector calculations, which then allows us to do efficient iterative optimization of this linear system. We turn off gradients at this point in our neural network. We just keep iterating till we get a solution. We're not trying to track the computation graph. We just keep going until we're within our tolerances. And this approach allows us to do really large matrices A. Even, what I showed you for the shallow water, a couple hundred on each dimension, this is, 10,000, right? And the point is, if the shallow water equation is 100 by 100, A would be 10,000 by 10,000. So it's no joke for a single neural network layer for a single batch element to invert that. Okay. So that's a forward pass, but we're building a neural network. We need a backward pass. And because we turned off gradients to do the iterative solve, we're not trying to unroll the computation graph through the entire forward pass. That would also have a very bad memory cost. We actually now need to do the backward pass and calculate gradients. So we need to differentiate backward with respect to, say, the input X or the parameters involved, and so on, which essentially means differentiating the solution with respect to the matrix and the vector A and B. So let's start with respect to B, right? AY equals B. Well, if we just do implicit differentiation of AY equals B, we get DDB of AY equals the identity matrix, because DB with itself is an identity matrix, which then we're differentiating with respect to B, so A is fixed. So we end up with A dy dB We invert that, we get A inverse. Okay, but we don't want to calculate input output gradients. We want to do backprop, which is to say, we know, suppose we know the gradient of the loss with respect to Y, we want to calculate it now with respect to B. So we use the chain rule here, the LDB equals the LDY times dydB. Now we know dydB equals A inverse, so plug that in. Then the LDB is a row vector. We have one element in the loss, and then we have a whole bunch of elements in B. Similar to LDY. So then we multiply by A and transpose, and we get A transpose times the loss gradient with respect to B transpose. Now it's a column vector equals this column vector. Now this is what we're backpropagating from the next layer, right? So we know this. We know the loss gradient with respect to Y. This is what we want. The loss gradient with respect to the constant term of the linear system. And now here, this is interesting, right? We end up with a new linear system to solve. This is the adjoint. So originally we solved A in the forward pass. We solved AY equals B. Now we need to solve A transpose times the unknown gradient of the loss with respect to B equals the known gradient of the loss with respect to the output that we already computed on the forward pass. So this is nice. This is basically a case of the implicit function theorem. And what it's saying is that we have to do one more iterative solve in the backward pass in order to get the backprop gradient. So you have to basically write a dot backward method for one of your PyTorch classes. And of course, A transpose has the same sparsity structure of A. So it's going to have the same kind of algorithms, iterative algorithms will work to solve it. And then I'm going to leave out the details because it's a bit of kind of the, not the fun math, but kind of the, okay, which index was that, which dimension was that? But in the end, if you look at the same argument with respect to the matrix, you get something very similar. And then indeed, you can say, all right, well, the matrix is actually built of these diagonals, and you can compute everything else with backprops. But the point is, because once you computed this, you can then compute this very easily. You don't have to do a second solve to do the gradient with respect to the loss. Okay, so we do one solve in the forward pass, we do one more solve of the transpose matrix in the backward pass, and this gives us linear implicit layers. Okay, but I kind of cheated a little bit, and then I said, okay, we're gonna solve it. It has the right sparsity structure, but that's not really enough. It's great if it has a good sparsity structure. Okay, then we'll be able to solve it efficiently. But what's a guarantee this actually even has a solution, right? These are learned coefficients. This is a neural network telling us what these coefficients are. What if they're all zero? What if we have 0 times y equals 1? I mean, it's not going to be solvable. So there's two criteria we want, right? One is A has to be invertible, or what's the point? And indeed, if you look at the other studies on implicit layers that have taken very different approaches, typically what they'll do is they'll have the identity function plus some Lipschitz function. They'll divide it by its spectral norm or something to keep it from growing too quickly, and then that's how they get invertibility. Instead, we're building a linear system with built-in invertibility. I'll tell you how in a second. So it's not unprecedented in the literature to do these implicit layers, but this is kind of a different approach. That was kind of more directly taken from the numerical solvers. So we want it to be invertible, but invertibility also isn't quite enough. For a lot of these iterative solvers, it is possible to kind of create these pathological examples where, yes, the matrix is invertible, but your particular iteration will just go on forever or diverge. So we want it to actually converge with an invertible A, but A and B are dependent on the input data X from the previous layer. So how do we actually do something about this? So we looked at the criteria for these different iterative linear solvers, and we find a lot of them have very good guarantees if you have what's called diagonal dominance, which is to say, if you look at each row of the matrix A, the main diagonal should have an absolute value bigger than the absolute values of everything else put together. And actually, if you look at the structure of the see if we go jumping around a lot, the semi-implicit scheme, you have here's your main diagonal term here, right? you have your Zn plus one, you all this stuff on the left-hand side, and then you have kind of west, east, north, south, these off-diagonal terms, but they are all multiplied by the time step. And what that's telling you, like in a lot of symbols or in a few words, that indeed the linear systems for the semi-implicit schemes actually become diagonally dominant with a small enough time step, which is, a special case of, yeah, your method will converge if your time step is small enough. So we basically just parameterize the neural network's representation of the matrix elements such that, okay, if we take all the off-diagonal elements of each row, we add up their absolute values, we add an exponential function of that, and then that's the main diagonal. So no matter what the network learns or fails to learn, the matrix is always diagonally dominant, and the number of iterations to converge might be data dependent, might change during learning, but it will converge every time. It'll always be invertible, and it will always converge with, say, the Gauss-Seidel algorithm, the Jacobi algorithm, the red-black Gauss-Seidel algorithm, the conjugate gradient. So we have some, free choice of these solvers depending on our problem, and we know that it's actually going to give a result. So in putting this together, this is what we get, right? So here's an example of a simulation from the 2D shallow water equations. Here we have the water height at one time point, and then we have the velocity x and velocity y. The particularly challenging thing about the system, and this is why you need the semi-implicit schemes, is you have closed boundaries. You can see the waves are reflecting off the walls and conserving energy. And if you look into kind of one small part of the height, you can see basically over time the way things move around, and these kind of fine spatial features are relatively important. And what we find then is that at all time steps we get an improvement for these linear implicit layers, but especially when we increase the time step to be bigger, which indeed is kind of the whole point of using a semi-implicit scheme, that you can use a large time step. We find basically that the CNN diverges, whereas the CNN with linear implicit layers, same number of parameters, a little bit more computation time, is able to maintain pretty good performance. And of course, the error grows with simulated time, just like in all these other examples. But we're able to get a pretty good match. And even when we do make errors, it still looks like a shallow water simulation and not like some numerical grid noise, right? So here's the original simulation with Bachhaus's semi-implicit scheme. We see, I think we started this with a delta function at 0, and maybe a little Gaussian bell, and the thing spreads out. There's nonlinear effects happening in various PDE terms. It's bouncing off the walls, and the waves are interfering with each other along with the nonlinear effects, and you get this very interesting fine pattern of everything happening on a small spatial scale. And we're able basically to capture that with the linear implicit layers in a regular CNN with the same number of parameters. And we did try a lot of different architectural tweaks before we realized what the issue was. You see these, visually it's very different, but you see these kind of grid patterns emerging, which are really typical of convolutional networks. So this was nice to see, and basically, what we're saying is that we took the idea of spatially varying coefficients of a linear system that has a local sparse structure. That's what a semi-implicit solver for the 2D shallow water equations does. We took that same logic, we put it into our neural network. We found a way to do backprop, and we found, perhaps somewhat unsurprisingly, that it was able now to imitate the system that it was inspired by much better. But, yeah, sure.
Maybe it's not relevant. Maybe a question regarding the implicit layer. In practice, you have to run a solver in each the forward pass and the backward one.
Yeah.
What's the effect that you may not reach the asymptotic convergence? In practice, you have a finite
yeah.
variables. Does that Does it resolve the convergence?
It affects it kind of the same way it would affect the original simulation. Yeah, I mean, one thing that we realized actually when we started trying to solve these problems is we had to turn our tolerances down on the original simulation, because otherwise it was just too discontinuous and almost like numerically stochastic. But so all these, the original simulation, right, it also has these linear systems and it's solving with the same method. So yes, I mean, you could say it's generally a limitation of any iterative scheme. I think.
But my question was more in the, I understand this, in terms of simulation, but then the impact or the consequence when you want to calibrate this. So, and the difference between because the implicit layer and the differentiate assuming.
Yes, oh, I see.
The minimum. My question is that, is there anything there that in practice you do not get the minimum?
No, we didn't. And so you're right.
You differentiate with respect to minimum, or you approximate the, all the.
Yeah.
This, do you have any insight?
I don't, all I can say is this is a very good question, right? Like when people set their tolerances for how many iterations, when are we converged, they're mainly interested in either the change in the solution or the change in the residual. But no one is thinking about the change in the computed gradient. And this is probably the more relevant thing for us. So it's actually worth asking, how big are those errors on the backward pass? Because I don't know that anyone's ever measured them. I know there's some work from David Duvenot's group in Toronto where they're interested in, they do a finite number of iterations and they're able to do this in a way that they get an unbiased estimate of the gradient. Without having to go all the way to convergence. More than that, I don't really know, but I think there might be some theoretical work on the errors involved. Yeah. Yeah. So, yeah, so this was one kind of inductive bias or computational strategy we could take from numerical modeling. Another thing that we were starting to work on, this is work by a postdoc in our group, Yunfei Huang. We want to apply kind of elements of geometric deep learning to these fluid dynamical systems, right? So we have a neural network with maps inputs X to outputs Y. There may be a set of transformations we're aware of where, you know, we have a symmetry group, say the simplest would just be translations, right? If we transform the input, we transform the output. I mean, a very simple example is convolutional networks, right? If your network is only convolutions and you imagine your input at everything is zero padded, so you can imagine your input image is actually infinite, it's just zeros beyond a certain point. Then if you shift the input, you're going to shift the output. This is already true, right? But looking at these PDEs, for example, the 1 and 2D shallow water equations, Navier-Stokes, a bunch of other ones, there are other symmetries, which may be related, for example, to reflections, to rotations. You have these on square grids, you have them on hexagonal and icosahedral grids. There are other symmetry groups besides translations. And there's been some really exciting work, mainly out of Max Welling's group in Amsterdam, but a few other places too, asking, can we build convolutional layers which respect these symmetries such that if you rotate your input or do a reflection on the X or Y axis, you do the same for the output. The answer turns out to be a little tricky, but doable. It's not like you have one output channel, you now have multiple corresponding to the multiple transformations in your symmetry group, and such that when you rotate the input, you're rotating all these, but you're also permuting them. And then at the end of your network, you do a reduction over the symmetry group elements. So you get the output is actually equivariant the way you want. So we've been trying this out a little bit in the 2D shallow water equations. It's very preliminary, but we're seeing a fairly big improvement in the quality of emulators we might train using the group equivariant convolutions, reflection equivariant in 1D or rotation in 2D. I feel there's got to be a better word than equivariant. It seems like unnecessarily long and complicated for a simple idea, but with symmetry respecting. So this is something we're working on, and other groups are doing similar things across a lot of different scenarios in earth science modeling. One thing you can do is, this was an interesting paper from Yuval and colleagues at MIT a couple years back. They say, okay, we want to train the neural network to imitate a process in an atmospheric model, which does some Moyes convection and other subgrid processes. And the problem is, if you just learn the time derivative of the concentration change of moisture, you're no longer going to conserve mass. You'd be creating and destroying more moisture everywhere. So instead, they learn fluxes, and then they integrate these fluxes to calculate tendencies. So by choosing the right representation of the outputs, and in some cases the inputs, are able to get the conservation laws for free while doing a data-centric learning approach. A similar paper from Seifert and Rasp that did warm rain microphysics, which we'll talk a little bit more about in a minute. The idea was, instead of learning time derivatives, you learn these process rates at which different kinds of droplets collide with each other and with themselves, and then you calculate time derivatives in a second step from these process rates. And this kind of forces the time derivatives to, for example, conserve mass and to maintain some other properties. So these are kind of rough ideas about, okay, can we try to take advantage of data-centric ML to build differentiable, flexible models that run well on modern hardware, but at the same time kind of take some of the good ideas and inductive biases from numerical physics-based modeling and put them into our data models. And so I don't know. We're making some progress in kind of going to more complex models. Our groups, others, I think here we've seen something a little bit further to right off this curve. But everyone's a very long way from kind of operational climate, weather, atmosphere, ocean models. So there's a lot of conceptual mathematical problems to solve. Machine learning is very difficult, and there's also technical problems about how data should flow around, and even the computation should be done at this scale. But okay. And then this gets to the third, and I think probably most speculative, but I think it's, when we're talking about emulation, I think it's worth mentioning kind of where I think this stuff will find and has found some of its most practically useful application, which is really looking at these big Earth system models and saying, I want to emulate this process. And I mean, this can be very useful. It can be a very powerful strategy, but it also has some pitfalls, which I want to mention as well. So we have this big Earth system simulation, or 500,000 lines of Fortran code. It has atmosphere, ocean, has a coupler. It has a bunch of parameterized subgrid processes, and yeah, who knows what else, right? Okay, we want to choose carefully which parts of these of this simulation we want to replace with machine learning. So first, you can distinguish between known and unknown processes, and among the known processes, there are ones where you can already compute them very efficiently. Then you might want an emulator to provide gradients, maybe, or maybe you just leave things alone. And then there are the ones which I think are probably the most exciting, you might say, low-hanging fruit right now, which are the cases where we actually trust our models reasonably well if we're willing to run them in a very high precision mode. But this high precision mode is too expensive to use operationally. And as a result, we need something which will not just provide derivatives that we don't have, but really improve the cost accuracy trade-off, right? So say, let us run the model with the computational resources we have at a higher grid resolution, or for a longer time, or let us improve the resolution, or let us maybe improve the accuracy and discard some approximations. And then, of course, there are other unknown processes I won't talk about this much, but where we really don't even have a simulation to learn from, and we have to go right to observations. I think this is a more difficult problem. All right, but the idea of learning specific parameterizations for subgrid scale processes has attracted a lot of attention across the geosciences in recent years. One of the first big papers was Ross PNAS paper in 2018, where basically that you showed that you can basically make a cheap model behave like an expensive one using one of these corrective terms, a simple setup in an aquaplanet, but still interesting. We're starting to see, this is using the kind of differentiable physics in Julia. We're starting to see learned parameterizations for turbulent heat exchange come out of that. We've seen stuff for radiation, moist convection, the Yuval paper I mentioned, Chantri's paper on non-graphic wave drag. They're really happening everywhere across all different fields of atmosphere and ocean science. But a common theme that you'll get is that the results might look pretty good when they, kind of say, how well does the emulator predict the next time step given the current one, while trying to learn some specific physical process in this big model. But being able to predict the next time step, well, doesn't mean that you're going to be accurate or even numerically stable when you couple your machine learning model to the rest of the Earth system simulation. And this is what I like to call this a coupling problem. It may have a better, more reasonable name, but the way a lot of these parameterization learning studies worked is you divide the model into what you want to learn and to what you don't want to learn. Everything else, which is all the other physics and dynamics. So you run the model, and then you store the inputs and outputs of the function to be learned. You train it offline to say, okay, here's my X, here's my Y, and I want to learn to map from X to Y using data-centric machine learning. And then after that training, you can take the ML parameterization and couple it back to the rest of the model. And you can say, well, actually, this was very expensive when I ran it in high precision mode. So now I'm 800 or 800,000 times faster. And I have very low accuracy on single time steps. But when you actually do the coupling, and then you run the whole thing together, you find that after a few months, you got completely the wrong climate. If you're lucky, it hasn't gone to 10,000 degrees, but in any case, it may have really given the wrong answer. And unofficially, I think I even heard this from Stefan Rasp around 2019, that they were just managed to find settings where their simple aquaplanet didn't do this. And the reason we're stuck with this is that it's exactly the problem that these deep differentiable emulators were aiming to solve, right? We can, during training, we can iterate over multiple time steps using automatic differentiation of the machine learning model. But when we're coupling to the rest of the model, we're still stuck in Fortran, C++, or what have you. We don't have derivatives. So we can't take into account what's going to happen over multiple time steps or when we couple to other processes during training. So what can we do about it? One idea that's been proposed and used to some success is the idea of single column and box models, where you do take into account the effect of the rest of the model, but only in one direction. For example, for learning atmospheric chemistry, we learn the effect of temperature, but we wouldn't consider the effect of the chemical reactions on the temperature field. It would just go one way. This allows us to self-iterate during training to kind of get better numerical stability, while still taking into account, at least in some crude measure, the dynamics and other physics. I don't know. I presented this idea or mentioned this idea at the user conference at the German Climate Computing Center, and all the guys from the Max Planck for Meteorology got up and said, we all know single column modeling doesn't work. I think it's better than this, but it may not really be the answer we need. There have been a number of studies which showed that doing the self-iteration during training, even if you just use a simple box model or a single column model, actually really increases accuracy and stability. even when you go back and then couple it to the full model. Why that is and when that helps and when that doesn't help isn't so clear yet. One of these is studies is on warm rain microphysics, which inspired a current PhD project in our group. Here, they didn't do this training, self-iteration during training, but they did at least go back and show that when you couple the trained model to the to itself, it doesn't reproduce the right time scales for the conversion of cloud to rain droplets. So we wanted to ask, can we do better than that? This is, I think, one of the most appealing processes to emulate in atmospheric models, because the really accurate representation is extremely costly. So you have, if you really want to represent this as accurately as possible, you'd represent the collisions of different droplets, and they coalesce into bigger and bigger droplets. The cloud droplets form rain droplets, they fall down. This is from Shima 2008, and it shows this kind of warm bubble scenario, and kind of red is big droplets and blue and even white is smaller droplets. And then if you look over time, you can see the evolution of the droplet size distribution. And so if you actually look in a weather or climate model, instead of these distributions or droplets, they basically have a threshold of about, I think, 12 or 15 microns. And anything below that's cloud, everything above that is rain. They keep track of the number and total mass of droplets below and above that threshold. So 4 numbers. So they break that distribution down into 4 numbers. And these 4 numbers are what's represented. They're what determines when it rains, and they're kind of determines the radiation balance that and how clouds contribute to that. So it's very limiting. And it's bad enough with warm rain. It gets actually much worse when you have graupel and snow and hail. It just isn't well represented in these bulk moment schemes. But here the task was, can we take those 4 moments, the mean and number of droplets below and above this 12.5 micron threshold, and can we emulate their time integration when we simulate when we generate our simulations from these expensive droplet simulations? Can we get an emulator to predict how these bulk moments, these 4 numbers, will evolve over time? And it's interesting because it's not exactly the standard emulation scenario we had before. For one, these droplet simulations are stochastic. You simulate them with the Gillespie algorithm. They're discrete, so they're really non-differentiable and non-deterministic. But even so, we were able to train neural networks to predict how these moments will arise over multiple time steps. We use box models and we use self-iteration during training, and we were able to correct most of the timing errors that Seifert and Rasp had observed using iteration just on 1 time step. So now we're starting to couple this back to the rest of the model and see how it performs. And we're trying to maybe take into account at like dynamics, that is wind during training, and maybe include aerosols, new hydrometeors. Another process which I think is really promising for replacement with ML, emulation with ML, are chemical schemes in the atmosphere, they're also in the ocean. And that's because you have these complicated schemes, right? I mean, even in a simple one, you might have 100 different chemical species and several hundred chemical reactions between them. So it's way up from the 4 bulk moments of the cloud microphysics scheme, and way up from our spatially homogeneous Lawrence 96. And because you have different reactions with very different time scales, you end up with a system of coupled ordinary differential equations, which is stiff. And as a result, you need these implicit and semi-implicit solvers, which again means you're solving a linear system at every time step. But it gets worse. You might actually want to do the time stepping in your outer dynamical model, your radiation time step, your advection and tracer advection, and momentum advection and precipitation. All this might be happening, I don't know, once every 30 seconds or once every 2 minutes. But to get accurate results from these schemes, you can see here's nitrate and and various oxygen species and ozone, and they're all driven by these incoming radiation. To get this accurately integrated, it's not enough to use these implicit solvers. You also have to use an adaptive step size. So to do one step of your model, you might have to do anywhere between 10 and 200 steps of your time scaling scheme for your chemistry. And that's, of course, for every vertical level of every grid cell of your model. And it's very unevenly distributed too. You can see the coupling, for example, to the day-night boundary, to the the time derivative of the nitride here. You see that it's decreasing as the sun comes up and increasing as the sun goes down, which means that these grid cells are going to require more iterations to solve their ODEs. It's a mess. So you have to do a ton of computation, to the point where if you want to do climate simulations, where actually this stuff is really important for predicting future climate, you just can't afford the full chemical scheme. So you have to use these gross approximations, or you have to kind of assume certain concentrations as boundary conditions. We just don't know the answer. The same goes for air quality forecasts and with high resolution around cities. We just have to make a lot of undesirable compromises. Well, okay, we have the right answer. It's just too expensive. So this is a prime candidate for machine learning as well. So we're starting to work on this now. I actually just started a project on it this year. And there's a considerable literature emerging as well. We have a study with random forests. We have some stuff with neural network, and a bit small here, but basically what you can see is that if you do this self-iteration during training in box models, you get an improvement. And if you take your initial conditions from a coupled run of the whole chemical scheme to your dynamics, you'll get even better results. So these are kind of the areas where I think differentiable emulators might make kind of more of a practical impact. We're not really solving the inverse problems we wanted to solve in the beginning. We're really just replacing them. But I think in both of these cases, one could go ahead and do data assimilation, tuning, and correction. But in these very low-hanging fruit, it's if you can just build the emulator and is halfway accurate and faster than these very expensive training data, you've actually made a pretty significant contribution to atmospheric research. So to sum up, what have we gone over? Started playing with these things. We saw that they could actually provide derivatives when we don't have them from the original simulation, just by learning from simulation data. We can make them better if we can come up with physical or mathematical constraints that come from our knowledge of the system, spatial invariance for convolutions, these group equivariant things, or this mathematical structure of the inverting a linear system. When we get to bigger systems, just kind of emulating the whole thing to solve inverse problems isn't going to scale, and we're really more interested in going for individual processes. It seems in our hands and others that one-way coupling during training can really improve accuracy, but when and why is not fully understood. And both in terms of, I think, mathematical tools, as well as the technical side of kind of software and components and workflows, we're just beginning to develop what we need to kind of build these simulations and emulations to be differentiable and kind of make the most use out of that capability. So thanks.
Any question, or I may suppose the recording exhibition? I may have one. You haven't, if I'm right, you haven't mentioned during your